All right, welcome back. Let's move to the second topic, which is the capacitive transducers. We will talk about a few examples on the sensors and actuators. So before we proceeding with other topic, let's take a look at what are the transducers. Transducers is a word that transfer different form of the signal into another form or different energy into another energy. Transducers compose of the sensors and actuators. So sensors are the devices that measure a parameter of interest. For example, humidity, temperature, vibration, displacement, etc. So usually they are non-electrical signals. This is generated from the nature. And the transducers need to convert those non-electrical signal and generate an electrical signal that then can be processed by the computers. So this is very important. Transducers will convert non-electrical signal into electrical signal. How about actuators? Actuators is in reverse way. They are devices that convert one signal into another form of the signal that can deliver to the environment or change the environment. So we call it actuators. So sensor, actuator form transducers. And many different types of non-electrical signal exist. Let's take a look at the figure in the bottom. Not only electrical signal, we do have the mechanical signal like velocity, displacement, acceleration, right? And the rotation, acceleration. We also have the thermal energy, right? Thermal waves, temperature, the thermal heat, and chemical, magnetic, even the radiation. So they are from the nature and non-electrical. We have to rely on transducer to convert it to electrical signal. What kind of electrical signal you have? Basically, it will be current, right? It will be voltage. It can be charge. It can be capacitance. It can be inductance or resistance, etc. Those electrical signal will be easier to process by amplifier, electronics amplifier, right? By filter, by the other types of the ADC, analog digital converter, digital analog converter, etc. So basically, they can be processed by our computer. So the transducers are generally referred to devices that convert one signal into another form of the signal. And signal is equivalent to energy. So you can treat transducer also the energy conversion devices, meaning that they not only convert type of signal into another, they also convert the energy into another form. Let me introduce a few important parameters in the sensors. First, very importantly, sensitivity. If you have the input physical phenomenon you like to measure, they will generate the output signal, right? We prefer small input to get large output, right? For example, it looks like you want to find a job that can earn you a lot of money. So you are looking for very steep I/O relationship. So sensitivity is actually the slope. Second one, offset. What is the offset? Offset is basically if you don't have input, you shouldn't have the output, but sometimes you will have the offset. So offset is required to be minimized. It's better to be zero. Then how about the linearity? Ideally, we like the I/O input and output to produce a linear behavior. That would be easy to design, easy to predict, easy to be used. But due to material linearities, structure linearity, geometry linearities, and even the transduction linearities, it will behave like this. So this is treated as the linearity where the maxima deviation from the linear response is defined right here. So in that case, in our sensor design, we prefer linear, make it as linear as possible. Finally, there is a very headache problem, drift. The drift means at different times, at different environment, you might have different sensitivity and different offset. Okay, so this is not allowable. At least their repeatability, uniformity, their reliability will not be good. So sometimes it will caused by the change in environmental temperature because different temperature, you might have a different Young's modules, different material properties. So that will give you different sensitivity and offset. But that is easy to solve based on what? Based on the calibration methodology or even using the lookup table. The most difficult problem to solve is basically drift over time due to material creeping, aging that you cannot predict. So the only thing you can do is to select the excellent mechanical property materials, for example, single crystal silicon. Anyway, this is very difficult to predict. In addition to sensitivity, offset, linearity, and also the drift, there are a few important parameters also in sensor community we should know. First one, selectivity. What is selectivity? For example, you are designing a chemical sensor, for example, oxygen sensor. The oxygen sensor not only responds to oxygen, they also have some response to, for example, hydrogen, right? O2 sensor, they also respond to H2, hydrogen. So the selectivity is defined as the sensitivity ratio between oxygen and the hydrogen. We like selectivity as high as possible. Otherwise, it would have cross-contamination, cross-sensitivity issues. Then another important parameter, we call it full-scale range, or another name, span. This parameter refers to the range of the sensor is supposed to measure. For example, you design a pressure sensor, right? And the pressure sensor in the spec, you should define it is measuring the range between 1 torr to 100 torr. So this is full-scale range or span. How about next one, resolution? Resolution is typically referred to the smallest possible signal that the sensor can measure, can detect, can distinguish. So the minima detectable signal or the resolution of the sensor is at the point where the SNR ratio, signal to noise ratio, equals to 1. You need to distinguish the signal out of the noise. Otherwise, it cannot be treated as the signal. So resolution is based on that. Next one, accuracy. Accuracy is defined as how accurately a given signal can be measured. Due to what we mentioned in the past, right? Noise, the drift of the material, and the other external influence like electromechanical interference or the other interference, the accuracy of the sensor usually much worse than its resolution. For example, you can achieve very high resolution, but it might not be accurate. So accuracy is one of the important figure merit in sensors. Next one, dynamic range. Dynamic range is defined the maxima allowable signal to the minima detectable signal. We already know. Minima detectable signal is referred to resolution. It will be dominated by noise. But maxima allowable signal is actually governed by the linearity. So dynamic range specifies the range of very small to very large signal that the sensor can capable of processing. Finally, if you are designing a dynamic sensor instead of the static or quasi-static sensors, for example, accelerometer or acoustic microphone, bandwidth is needed to be considered. So it defines the maximum detectable signal frequency. For example, in acoustic microphone or speaker, you have to cover the frequency from 20 Hz to 20 kHz. That mimic our ear membrane of the human beings. Alright, so with that sort of the background information for sensors, let's take a look at how we can use the capacitor to serve as the transducer. There are two main types of the capacitive transducers. First one, we call it variant gap capacitive transducer. The second one is the variant overlap area. Think about the equation for capacitance. It comes with the dielectric constant times the overlap area divided by the gap spacing, right? So for the variant gap, we actually change the gap spacing of the capacitor to change the capacitance. For variant area, we actually change the area, okay, to vary the capacitance. So based on that, if we design a tactile sensor, you have the fingers, right? This is your nail. You press it down, or you have a finger, you push it to the right. They will generate different kinds of the sensitivity. One side, you are going to push down your floating membrane, right? Your floating top electrode. The other case, you are going to put the horizontal motion of your top plate. So that will corresponding to variant gap and variant overlap area sensitivity. So in this case, we take a look at how much deformation leading to how much capacitance change. So we call it a capacitive transducer sensitivity. It is approximated, inverse proportional to the D squared. So if we are using the MEMS process, the D is only 1 micron or even lower than 1 micron, your sensitivity will go very high. As compared to variant gap, for the variant area, it's proportional to 1 over D. So the sensitivity is not as high as the variant gap. But all the efforts, all the design, all the performance will be the trade-off. For high sensitivity variant gap transducer, they suffer nonlinearity because their gap change will associate with their sensitivity. But if your plate move to the horizontal direction, the gap is a constant. So you will have a fixed sensitivity. So one final comparison. In the left-hand side, variant gap, high sensitivity but very nonlinear. In the right-hand side, variant area capacitive transducers, they have a constant sensitivity, which is good, but they have limited sensitivity. So transducer gap is the key for capacitive transduction. Let me go one step further. In a capacitor, especially the top plate can move. They will become the MEMS capacitor because one of the plate can move. So in this case, it will become an electromechanical energy storage device. For example, this is a capacitor and their plate can move. So they will generate a variant capacitance, right? So at one side, they deal with voltage and current. At the other side, due to motion, they also deal with the force, Newton force, and the velocity. So using a simple electromechanical analogy, you can treat voltage as the Newton force. This is E field, right? Electrical, this is mechanical domain. So V can be equivalent to force. The current can equivalent to the mechanical velocity, and the charge, which is electrical displacement, also can be equivalent to the deformation or the displacement of the sensors. So use that, the capacitor will generate two poles. One represents electrical parameter, double E domain, right? Voltage and current. The other side, they deal with the Newton force and the velocity. So they are energy conversion. They can convert electrical energy to mechanical or mechanical back to electrical. Okay? So this is the single capacitor. The only difference as compared to the double E capacitor is one of the plate will move. So they become MEMS capacitor. And such kind of the stored energy shown here, this is the work, right? The energy stored in the MEMS capacitor, including mechanical part and electrical part. They can serve for both sensing and actuation purposes. One more thing we have to add into the modeling is your top plate moving part cannot be floating in the air. They need to support by certain structures. For example, cantilever beam or the membrane, right? Moving membrane. So that can be modeled by mechanical spring, K, spring constant. They need to be support anyway. Assuming the movable plate is connected to the spring with a spring constant K, you will form a full analysis of the capacitive transducers. Remember, in the previous slide, our sensitivity from the deformation to the capacitive change, it will be equals to epsilon A over D squared, right, for variant gap. You can move the displacement into the right-hand side and replace the displacement by mechanical Hooke's law, right, F over K. So in this case, we will be able to link the signal of interest, which is the force, right? If you like to design the force sensor, you like to measure the force and lead to the capacitance change. So the other parameter will become a sensitivity of this sensor. One more time, if you have a finger, you will press your plate moving down, it will change the capacitance. How to measure the finger force? Easy. If you got the capacitance change, you times the sensitivity and also the spring constant, then you got your force. It becomes force sensor. Same way, if your finger push your plate to the right, this will be defined by the overlap area capacitive transducers. So remember, in previous page, our sensitivity comes from epsilon W over D, right? Okay, can you move the deformation into the right-hand side? Then replace by the Hooke's law, Fy over K. So you can link the major capacitance change versus the signal you like to measure in this case. So that will form a full analysis of the capacitive transducers. Using above background information, for example, we already covered variant gap capacitor and variant overlap area capacitor. Remember, one more review. High sensitivity but non-linear. This is low sensitivity but very linear. So they have their trade-off. So you have to find out which one is suitable for different applications. Using that, we can develop force sensor, for example, tactile sensor. We can have the pressure sensors, okay, like accelerometers, either vertical or lateral or 3-axis, like acoustic microphone, and finally the humidity sensors. So we will go over those examples very quick because due to the limited time. So let me introduce first the capacitive force sensor, which is a tactile sensor. They developed by a process called DWP, dissolved wafer process. Due to the limited time, I will go quickly from the process point of view. You start with the silicon wafer. You can have a hard mask on top, right? And you perform the KOH, wet etching. So it will have what? It will have the anisotropic etching using what? Orientation dependent philosophy. So basically, they will create some cavities. And then you go to the furnace to perform boron diffusion, which is the doping process for most of the CMOS fabrication process. So those regions will be heavily doped. They have a lot of boron inside. Then the third step, you perform shallow doping, either using shorter time or using the ion implementation. You can have a very shallow diffusion of the single crystal silicon. Finally, you flip 180 degree using the silicon glass bonding, bond to another glass wafer, and they already have the bottom metal electrode to form the capacitive transducer. Then put it into the KOH. So all the substrate will be dissolved in the KOH. So we call it dissolved wafer process. Using this technology, you will have a single crystal membrane structures supported by the anchors. And you can see that in a transparent glass wafer, you have more than 1,000 element capacitive silicon tactile sensor imager. So it's a 32 by 32 pixels. When you press it, you will see different folds distributed in the array. So you can actually sense the profile of your stress in terms of the force. And it's about the size of the one dime. Another example is the capacitive pressure sensor, in addition to the tactile sensor we just mentioned in the previous slide. Very thin and flexible diaphragm, it will deflect. If the outside pressure and the cavity pressure are different, it will be deflect. So when they deflect, they will change the gap spacing. As we know, the delta C over delta X will be, in this case, epsilon A over D squared. Right? So when you actually change the gap spacing, you will change the capacitance. So in this case, it can be read out by using the silicon electronics, for example, the charge amplifier. So the flexible membrane deflects in response to the changing pressure. So they can serve as the pressure sensor, ambient pressure sensor. Diaphragm separated from a fixed electrode by a smaller gap. Smaller the better. You will get a higher sensitivity, but they will become more nonlinear. So the diaphragm deflects, then the capacitance change. So this change can be measured electronics using the amplifier. So you see the silicon electronics will be located in the other part and a membrane at the center part. Okay, so that will form a pressure sensor. Two types of pressure sensor we can design. The first one will be relative pressure sensor. Relative pressure sensor, they only measure the difference of the pressure in and out. Okay, but more useful one will be absolute pressure sensor. To enable absolute pressure sensor, we need to know the pressure in the cavity in advance. How? You can seal it, right? It can also be vacuum. So with known pressure, you can extract the ambient pressure. So it will treat it as the absolute pressure sensor. So the CMOS barometric pressure sensor in a couple of decades ago is developed in Michigan. You can see that on the top lid, it will be glass wafer. They already deposit the top electrode and also the shielding of the metal. Then at the bottom, silicon wafer, this is a silicon wafer. They are using the bulk micromachining. They can produce a membrane on top of the cavity, which is a vacuum package. So they will generate the absolute pressure sensor. And all electronics can be located at the center recess area, shown right here. So this is the top OM view of the silicon electronics. They have the analog readout, they have the digital circuit, they have the on-chip sample and hold for the ADC. So they can perform a lot of different functions. For example, like compensate the gain and offset that we just mentioned in the very early through the electronics. So if you like to measure different pressure range, full scale range, right? You have to design different membrane size. For example, in 1 atm ambient pressure, that is treated as a large pressure range. You need to use a smaller membrane because smaller membrane, they are stiffer. They are stiffer to accommodate the high pressure. But with very low pressure region, you might use larger membrane because they are more sensitive. So using different size of the membrane, you will be able to cover the full scale range, the full span of the sensor requested by the customers. In addition to membrane, let me introduce the very common use accelerometers. The accelerometer might have a little bit more mathematical analysis. So let me start with the system, the modeling of the accelerometer. It consists of proof mass, mechanical spring. The mechanical spring can be cantilever beam. And inside you do have the air, so they may have the damping, okay? Based on second order motion equation, based on the force balance conditions, you can have the system's inertial force, MA, damping force, B times velocity, and spring restoring force, KZ, right? Equivalent to external force, which is the signal of interest. For example, let me make a quick example. If you have a car, right, this is your car. You are driving right here. There's a wheel in different rows. The car will shaking up and down due to the roll, and you are going to measure using the accelerometer to measure the acceleration in Z, right, for the car. So what you're interested is Y double dot, right, acceleration of the car. And for the sensor output, this is the gap spacing, capacitive gap spacing. So Z is very important. So we are going to use the governing equation to derive the transfer function from where? From the car to the capacitive transducer gap. So with the full analysis, you can have their amplitude ratio versus the phase ratio. So R is treated as the normalized frequency, which is the frequency divided by the system resonant frequency. So this is normalized, no unit. So based on the static relationship, you find out that Z over A will be M over K. One more time, remind you one more time. A is the acceleration we like to measure. Z is the capacitive change, capacitive gap change we like to get. right? It will be proportional to m over k. That means if we would like to enlarge or enhance the sensitivity of the accelerometer, we need to design huge proof mass and also very soft spring, okay? But take a look at the resonant frequency of this second order equation. It's root k over m, right? It's root k over m. So their bandwidth will be limited by root k over m. So if you like to increase the bandwidth, you actually sacrifice your sensitivity. Or if you like to have high sensitivity, it will limit your bandwidth. So that is certainly a design trade-off. Using this equation and their results, let's plot the frequency versus the transfer function. Frequency in x-axis, the y-axis will be the transfer function. The transfer function we use right here is the car displacement versus the gap change, right? You can make some derivation, finally find out the car acceleration and the capacitive gap modulation is based on this equation. For very low frequency, which are approach to zero, right? 0, 0. This becomes 1. You will find out in low frequency operation, the car acceleration is proportional to the gap change, which is desirable for accelerometer design. How about at their resonant frequency? At their resonant frequency, basically you will find out there is a huge gain distortion. So not suitable for accelerometer design, but very suitable for high Q resonator, oscillator, and filter design for RF MEMS. So this is for RF MEMS. For very high frequency, go back to this equation. Very high frequency means R approach infinity. So infinity square, this is the infinity square, right? So in this case, this will approach to 1. So you will find out R frequency very high, Z over Y becomes 1. So gap change directly sense the car displacement. That is used as the vibrometer, which is called sense the vibration sensors. So different frequency range that belongs to different sensor. One more time, low frequency one suitable for accelerometer. The resonant frequency is suitable for high Q RF MEMS, and very high frequency suitable for vibrometers. So using the equation I just showed right here, we can plot another figure showing that Z over Y double dot, right? Acceleration of the car to the capacitive gap change. It can form a response, frequency response like that. For very low damping, not good. You have the sensitivity distortion at the very beginning, right? But for damping ratio too high, they do not have any bandwidth. So we have to control the damping, which is the pressure inside the package at 0.7. That will make you have a very wide bandwidth, checking to a certain value to make your spec. Okay, so this is a desirable. So accelerometer packaging cannot be vacuum, not like the pressure sensor in the previous page. They need to be packaged using a suitable pressure inside the cavity to have a larger bandwidth. So let's move to the application of the accelerometers. Based on their application, for micro G to 1G, we use those specs to perform navigation and the space. For a little bit larger, for example, like 10 milli-G, right, to 100 milli-G, they can be used for head-mounted displays. For 1G range, medical application, automotive. For very high G, for example, like shipping, handling, asset monitoring, for example, like FedEx, UPS, they need to check, right, the acceleration of the shipping goods. So they need to have a high G sensor to perform the measurement. Even higher G is needed for weapon, right, smart ammunition and the shock sensing for the mineral exploration. So they have different specs. One example, automotive grade inertial sensor and the inertial grade accelerometer, they have different specs. For example, inertial grade for satellite, for navigation, they need to have a very low resolution and also very low off-axis sensitivity. But for automotive, it's medium, right? Once the resolution lower than 100 millig of axis, about like a 5% can serve as the automotive. And another grade is even lower spec, which is the consumer grade. That has been used in our cell phone and also wearable devices. So the capacitive accelerometer here, we also implement two different kinds of the transduction mechanism. One is the variant gap. The other is the variant overlap area. And together with the mechanical model, the proof mass, spring constant, and the damping. Features of the capacitive accelerometers. They provide high sensitivity, right? Low noise. The reason why they have the low noise is because capacitor, not like resistor. Resistor is the noise source, but capacitor ideally they do not have any noise, so they can perform low noise sensors. Due to capacitor, you cannot through a DC current, so ideally they have a very low DC power consumption, and also simple structures like that. This is up and down for accelerometer, right? Z-axis. This is the implant. They can detect X and Y. They have high resolution. Again, we already talked about in sensor spec, right? The resolution is dominated by the noise. If they have a low noise, actually they should achieve high resolution due to signal to noise ratio, right? And they will have a better accuracy. So this is good, this is good, this is also good, but you need the circuit designer, right? More efforts on complicated circuit, real circuit. They also sensitive to parasitics or electromechanical interference. So bad and bad, right? But capacitor also not like a resistor. They are not sensitive to environmental temperature. So they have a smaller temperature sensitivity. That means it can accommodate different operation in different temperature. Okay, this is good. And they support closed loop and open loop operation. So closed loop, you can have a force feedback loop to enhance the dynamic range. So fabricated examples from the University of Michigan. You can see this is a single chip micro machine silicon accelerometer. In this process, they combine bulk micro machining and also surface micro machining. So the bulk micro machining, you can see their proof mass M is really huge. It is actually accommodate the whole thickness of the wafer, for example, like 600 micron thick. And they have the top electrode, stationary type electrode formed by surface micromachining. So in this case, their sensitivity is proportional to M over K. You can imagine they can have very high sensitivity due to, first, M, full wafer thickness, very large. K, thin film. This is a thin film, right? So they have a very low K, high proof mass, so sensitivity very high. So they can resolve even the micro G for seismic applications. So take a look at their sensitivity. In the X, let's take a look at the X-axis, blue curve, X example. The X-axis will be G, tested. Y will be capacitance change, delta C. So you can see that around a picofarad per G is really high, okay? Due to what? They are using bulk micromachining to enable a huge proof mass. Also, they're using surface micromachining to produce very low K, low stiffness mechanical spring to enable very high sensitivity in their accelerometers. So for designs, previous one is the Z-axis. Then let's take a look at the designs for lateral sensitive accelerometers. Left-hand side, single-ended devices. Right-hand side, differential devices. Let me introduce why this is a single side. Take a look at the fingers. If you have a moving part moving up due to acceleration applied, you will change the gap. For example, their gap go down, actually their C go up. That is the single end. But if you have an electrode 1 and electrode 2 at the same time, when you have a moving part, move up, right? So the D go down, C1 go up. The D here go up, C2 go down. So you will have a differential output. One electrode sense capacitance increase, the other electrode sense the capacitance decrease. Why differential is beneficial? First, they provide double gain sensitivity, right? Second, they can cancel common mode noise, so allowing you to eventually have a higher SNR ratio, signal to noise ratio. So about their model, you can treat these two capacitance as the variable capacitor. When your probe mass go up, one gap go up, right? C go down. The other gap go down, C, this is go up. So if you have a full bridge, full capacitor connected in the full bridge, you will be able to sense this node, sense these two nodes. So in this case, V go up. This case, V go down. Based on charge equals to C times V, right? So charge maintain the same. If your C go up, V will go down. So you will have a delta V in these two terminals. In terms of the system developed program, the diagram, one more time, you have the MEMS accelerometer right here, right? Then you can have a full bridge, two fixed capacitor, two moving capacitor. One go up, one go down. So that will generate these two nodes has a delta V because V will be differential. Through the integrated circuit, a comparator, and also very simple digital building block flip-flop, you can have what? Analog output. You also can have digital output, right? And the digital output is implemented by using pulse width modulation. Further better advantage is you can leverage the digital output, provide additional voltage as a feedback force, go back to your structure. So that will perform force feedback to enhance the linearity and also the dynamic range of your developed accelerometers. So this is the basic principle, working principle for analog device accelerometer families. So in Michigan, they developed 3-axis monolithic accelerometer using one single wafer process. You can see that this is for x-axis accelerometer, this is y, and this is a z. Okay? They are all aligned well in one wafer. And take a look at their OM view. You will see that all x, y, and z are aligned using polysilicon connectors. So in this case, their cross-axis sensitivity will be very low since they already align in the wafer lithography process. And for accelerometer commercialization in ADI, their XL families, you can see their history. They will from a MEMS accelerometer using the polysilicon surface micromachining technology, surrounded by all different electronics. And the next generation, they can shrink down the footprint of their circuit. Then even the advanced technology is they can produce the Y and X at the same chip surrounded by the electronics. So that is kind of the progress of the commercialization of the accelerometers. Now let's move to acoustic pressure sensor, which is the microphone. So you can see a MEMS microphone is simply pressure sensor, but they are not static pressure sensor like we mentioned barometric pressure sensor. No, they are dynamic pressure sensor. They have to respond to the dynamic acoustic pressure generated by human beings, right? So such a pressure sensor need to have certain bandwidth, as I mentioned, to mimic our human being ears, where the sound pressure need to be within the range of 1 millipascal to 10K to 10,000 pascal. And their signal frequency need to be 20 Hz to 20 kHz. Above 20 kHz, human being cannot hear. Then we can call it ultrasound. But for acoustic sound, we need to set this kind of spec in order to have a useful applications. So the bandwidth need to be large enough to enable to respond the relatively fast changing acoustic pressure sensor. So bandwidth is important. The microphones are fabricated using the capacitive transduction technique. It's called condenser microphone. Condenser microphone, another word, is the capacitive microphone. So if you have acoustic pressure generated by human beings, that will kind of impact the thin membrane, allow them to move up and down. So those motion will change the gap, right? And this is a button electrode of the capacitive transducers. So this is again a variant gap capacitive transducer based on delta C over delta X with the sensitivity of epsilon A over D squared. So if you make the gap spacing small as possible, you will be able to enhance their sensitivity. Okay? So in order to provide sufficient bandwidth for those capacitive devices, one important thing is your button electrode cannot be a plate. It needs to be a perforated backplate. Why? If you have the whole plate, the air inside will be trapped. There's nowhere to go. So the acoustic pressure will impact the deformation of the membrane, but the membrane need to squeeze the air. That will limit their bandwidth. So you need to make some holes, allow the air go in and go out, corresponding to the dynamic pressure of the sound. Okay, so perforated electrode is important. Then this is a MEMS microphone fabricated using the polymer bonded wafers. You can see that silicon wafer at the backside is removed by DRIE, the deep reactive ion etching, till the diaphragm. And the diaphragm will be vibrate since it's very soft, corresponding to the acoustic wave. And they need to be detected by the button electrode, which is perforated. You have to make a hose, allow the air go in and go out, right, to enhance their bandwidth at least to 20 kHz to meet the spec of the microphone. So fabricated microphone, this is the dynamic pressure sensor. One more time, you can see that the whole membrane is actually consists of 6 millimeter by 6 millimeter, only 2 micron thick, very, very thin. So the stress control is very, very important. Once you remove the membrane, you actually can see the perforated electrode. They have a lot of holes. We call it damping holes. They allow the air go in and go out when membrane are moving. Okay? So you have to make sure that the diaphragm stress is controlled in mild tensile. Otherwise, the membrane will become buckling. So a lot of detail and a lot of know-how will be in fabrication side to fabricate such large membrane, sustaining diaphragm. All right. So the final capacitive sensor I would like to introduce is the humidity sensor. We already play area change, also play gap change. One parameter we haven't touched is actually dielectric constant. If we can leverage the change of the dielectric constant, we also can leverage the change of the capacitance. So this is the fundamental working principle of the humidity sensor. So far, what we discussed in the past will be either gap change or the area change, right? They are rely on moving part. But it's also possible to make capacitive sensors by using fixed plates, which no moving part is required. Then they will give you a better repeatability, reliability, and also the lifetime. So the humidity sensor work as you need to have one button electrode and one top electrode. And top electrode is made by finger. Allow the moisture go into the dielectric material, in this case polyimide. So polyimide will absorb the water molecule inside and also change the dielectric constant. Okay? So with that, you see relative humidity as the x-axis. Y-axis capacity change will be based on the permittivity change. So the water molecule go in, they will increase the epsilon, also increase the capacitance. So you can have the output and input quite linear in this case. So that is the working principle of the humidity sensors. Final part, let me quickly introduce the capacitive actuator. As we mentioned in very beginning, we have a MEMS capacitor, right? MEMS capacitor, only difference is the top plate can move as compared to conventional CMOS capacitor. That floating membrane need to be supported by mechanical spring. So that's what we know in the sensors. But we can store the energy inside the electromechanical energy storage devices, MEMS capacitor. They also generate electrostatic force based on this equation. So you can see no matter you have positive charge, negative charge on top and bottom respectively, or you reverse it, you have negative or positive charge on top and the bottom. They will be square. So no matter positive or negative charge, they only generate one-way force, which is attractive. So in electrostatic capacitive actuator, they only generate attractive force, no repelling force. It's not like a magnetic force, you can have attractive and repelling force at the same time. No, it's only attractive. So this is a very special feature of the capacitive electrostatic force. And we can also make such a system, okay, as a two-pole electromechanical energy conversion. So with voltage in, you can generate force, you can generate displacement based on what kind of spring constant or compliance you have. Or you can, on the other side, to change the mechanical properties, influence the electrical voltage and current. So that is the basic fundamental principle of the actuators. What kind of actuators we have? We do have some example to show. For example, TI, Texas Instrument, DMD. There is a micro mirror on top. We designed the torsional spring. So it looks like you have a plume mass, you have a torsional spring, you might have an air damping, right? Two order motion equations. Then if you apply different voltage, they will generate electrostatic force to pull the plate down or to pull the plate in another orientation. So that will enable a movable micro mirrors for display applications. Or you can treat the membrane as a resonator. If you apply the AC signal to drive the membrane, it will generate acoustic wave, for example, like speakers, right? So it will become actuators. And also, using this kind of mechanism, you can generate RF-MEMS switch, on-off switch, 0 and 1. So you can see that. Remove the mirrors, you will see a lot of mechanical spring, okay, torsional spring underneath. And for acoustic actuators, if you apply large voltage, you will snap the whole membrane down to the bottom electrode. So they actually in contact. So that can perform not only acoustic speaker, but also MEMS switch. So I think I have already covered the capacitive sensors and actuators, including the variant gap and variant overlap area, and also named a few examples. For example, the pressure sensors, the accelerometers, the acoustic microphone, humidity sensor, even the actuators. I think those materials will be very useful for your future career. Thank you.